Chapter 7, RE and R naught or R0. R0 is what's called the basic reproduction rate. That's actually a theoretical quantity. It has to do with the how fast a virus will spread with no prior immunity assumed. That's a theoretical figure that actually is not that practical because there's usually some immunity in a population, either due to prior exposure to viruses or possibly genetic immunity or some other reason. RE is the effective reproduction rate actually observed in the population. So that's generally a lower number than R naught. One interesting fact, RE is what they use in the UK. RT is apparently what they use in this country. But when I put this book together, I could find no references to this in the United States. It seemed like Google was censoring all epidemiological math. They had to find information from the United Kingdom or England. So I went with RE, but if you read papers in this country, we'll call this R sub T. R sub T is probably a better figure because T stands for time, and this actually is a function of time. It changes as we progress through a virus. This is a static figure. R naught would not change, but RT changes with time. So a couple interesting formulas. If X is a fraction of a population that's susceptible, now let's suppose 50% of the population is susceptible, 50 is not, then you multiply that fraction times R naught and it gives you RE or RT. And the fraction we must vaccinate for equilibrium is 1 minus 1 over RE. So this is pretty important because as RE increases, this fraction increases as well. So for instance, measles, we have to have a very high percentage of the population immune for the vaccine to reach equilibrium, where basically it's just it's progressing at a constant rate. If RE is really small, like with a normal flu, then we don't have to vaccinate as many. This is one way in which COVID is different from the flu. It spreads a lot quicker. So if we were to try for herd immunity, we'd have to vaccinate a much larger percentage of the population than with the flu. And the fraction without immunity is 1 over RE. Here's a simple calculation. Let's suppose RE is 2.2. That was an initial estimate for COVID. Then 1 minus 1 over RE is 1 minus 1 over 2.2, which is equal. Let me get my calculator out. 1 divided by 2.2 equals, and we get roughly 0.55. So we would have to, if the basic reproduction, or if the effective reproduction number was 2.2, we have to vaccinate 55% of the population. And that would actually get this reproduction number down to 1. Now 1 over RE is just this percentage right here, 1 divided by 2.2. It's a complement of that. Well, it's 0.45. And this is the percentage that would be susceptible. This is the percentage that we would need to vaccinate. Now, if you multiply 0.45 times 2.2, 0.45 times 2.2, and guess what? Because of rounding, well, we ended up with 0.99. That's pretty close to equilibrium would be 1. If we had a reproduction number of 1, it means basically every infection replaces itself with one infection. So if you have 1,000 infections in a population, you can come back a few months later, you still have 1,000 infections. It progresses with equilibrium. So on the other hand, let's suppose we have 5.5, then we do 1 minus 1 over 5.5, which is equal 1 divided by 5.5, and we get 0.82. And now 1 over that, it's just the complementary percent of that, 0.18. And if you multiply 0.18 times 5.5, you end up with about 1. You can multiply 0.18 times 5.5, and you get the same thing, 0.99. We round it off. So this is how much we would have to, there's two things that could happen here if we want to reach equilibrium. 5.5, by the way, is one estimate for COVID. Probably around that in a city, for instance, an urban population. To reach equilibrium, we'd have to 82% vaccinated or sick and recovered, assuming we have some immunity. So that's one reason why herd immunity for COVID could be a very difficult thing. If 82% get COVID, there's going to be a lot of people in the hospital. The hospital system's probably going to get overrun. It's just unmanageable. It's not going to happen. We can't reach herd immunity just by infecting everyone. Our hospital system would probably collapse at that case. And then if you go to the hospital for a broken arm, there's a good chance not going to be anybody there. So you'll just have to live with it. So, okay, that's the first video for Chapter 7. We'll be back with another short video as well that covers the second problem set.